Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we are going to show, or I'm going to show you how to find the pH of a weak acid when you're given the Ka value as well as the concentration. However, the initial concentration. However, the X is too small, approximation will not work, and I'll show you what that means. Okay, so the first thing you want to do is write your balanced equation. Oops, I forgot to change the acid here. So that acid is HClO2. Okay, so chlorous acid. So we have HClO2, it's going to react with water to give you H3O plus and ClO2 minus. Okay, so if they don't give you the balanced equation, then you've got to figure that out yourself. You got to know, of course, what the formula of the acid is and how it's going to react with water to form your products. It's pretty straightforward for acids. So the next thing is you want to set up your ice chart, and then you're going to figure out what the initial concentrations are, the change, and then the equilibrium expressions for those concentrations at equilibrium. So the first thing you want to do is write out, oops, let me make sure I have the initial concentration correct. It is a 0.1, so this should be 0.1, so 0.1 molar solution. Okay, now that we have that set up, so our initial concentration is going to be 0.100 for our HClO2. We're going to ignore water because water doesn't end up in our equilibrium expression for the acid, our acid ionization constant. So because again, we're looking at concentrations, the concentration of a liquid doesn't change, so this doesn't go in there. So we're going to ignore that. And then this is going to be our hydronium is going to be 0, approximately 0. And then this is going to be 0 as well, because there's hardly any H plus in there to begin with. There is some, but it's negligible. So approximately 0. So at this point, we're going to do our change. Obviously, it's going to go in this direction, so we're going to lose some product. It's all it's all 1-to-1 ratios here. So it's going to be a negative X. So we're going to lose some of our reactant, our acid, but we're going to gain the same amount of our H plus, hydronium, and we're going to gain the same amount regarding the anion here because of the 1-to-1 ratio in the stoichiometry. Now all we do have to do is add these columns together. So I take 0.100, subtract X. So there's that expression. And again, this is just going to stay plus X plus X. So now that I have my equilibrium expressions, I can plug that into the Ka expression. So here, Ka is going to be equal to the concentrations of the products, which is H3O plus, concentration H3O plus the concentration of ClO2 minus over the concentration of the acid HClO2. And so now we just plug in our expressions here. So since both of these are X times X is X squared over, and this is going to be that expression there, so 0.100 minus X. Okay, so I'm going to go through the x is too small approximation. So again, what that approximation is that I assume here that x is too small. So, which means that I assume that x is so small that it's not really going to make a difference in the original concentration. So if I subtract x from 0.100, it is pretty much still 0.100. So I just get rid of x. And the great thing about that is the reason I do that is it makes the calculations a lot easier. So whenever you can do that, do it. But in this case, we'll find out that you can't do that. So again, we have to put this equal to the the equilibrium constant for this, and the equilibrium constant is 0.011. So it's 0.011. So you can tell right away that this is not going to be it's not going to pass the mustard with regard to the x is too small approximation, because when you compare the amount of the concentration of the acid, the initial concentration of the acid, to the Ka value, this is 1.0 times 10 to the negative 1. This is 1.1 times 10 to the negative 2. So it's only like a factor of 10. It only differs by a factor of 10. So that's too close. So it's most likely not going to pass, and we'll see that it won't. If this was me, I wouldn't even bother with it. I would just solve the quadratic in this case. But let's just go through it and see what happens. So when we solve for x, all I'm going to do is multiply both sides by 0.100, take the square root of both sides, and then I get x. When I do that, I get x is equal to, where's x? Okay, x is going to be equal to 0.033. So 0.033. Now if I take this and divide it by the the initial concentration, which is 0.100, multiplied by 100, and I get, that's going to be 33%, I believe. Yes. So I get 33%. So this is definitely not less than 5. So the 5% rule is that this percentage, when I take my x value that I found divided by the initial concentration multiplied by 100, it should be less than 5% for it to be valid. So obviously 33% is not less than 5%. So this x is too small approximation is not valid. So in this case, what you're going to want to do is either solve the quadratic formula, or you might do a the method of just plugging it in. I'm blanking on the name. What is it called? Let's see. Successive approximations. So the successive approximations is where I would take x, right? My x value that I get. Like, so where's my x? My x value here. And I would plug it into that x there and solve for x again, right? And then I would keep doing that successively until the x values don't change. So after one successive after each succession, my x value should be changing, but at some point the x value isn't going to change. I'll get one x value, and then I do it again, I get the same x value, or very, very close to that x value, and then I can stop. That would be my x. But in this case, it would be easier to do the quadratic. So just solve this quadratic formula, I'm not going to go through how to solve the quadratic formula. You should know this. So when you do that, your x value is going to be, you'll get an x value of either negative 0.28, or is it 29? Sorry, 39. So you're going to get negative 39, or you're going to get a positive 28. Obviously, you can't have a negative concentration, so you're going to get rid of that one. So the answer would be x is equal to 0.28. So now you know what x is. You got your hydronium ion concentration. Now you can figure out the pH. So then you would take the negative log of this, and when you take the negative log, you get a pH of 1.55. So then the pH is equal to 1.55. So that's how you figure out the pH of a weak acid when you're given the Ka value and you're given the initial concentration, but the X is too small, approximation doesn't work. So I hope this is helpful. If you like my videos, please like, share, subscribe, put a comment in the comment section, and hit the notification bell. Thanks for joining me. I'll see you next time.